Now see the degrees of freedom of gaseous molecules. Yesterday we started discussion about this topic. So the motion of atoms and molecules is generally described in terms of the degrees of freedom which they possess. The molecules possess what? Some degrees of freedom. Okay, so the degrees of freedom will explain what the motion of the atoms and motion of the molecules in the gases and liquids and solids. Okay, the degrees of freedom of a molecule are defined as the independent number of parameters, required to describe what now the state of the molecule completely, Okay, so now to describe the state of the molecule completely, we need what? Degrees of freedom. What we need? Degrees of freedom we need. Okay, when a gaseous molecule is heated, so that is when gas is heated, the gas molecule absorbs what? The heat energy. The energy supplied to it may be bringing about what now here? It may bring about three kinds of motion in the molecule. In the molecule, there will be three kinds of motion when the gas molecule is heated. Okay, different gas molecules possess what? Different types of degrees of freedom. Okay, so they have three types of means for motion here. First one is what? The translational motion. Means the motion in straight line. The motion along straight line is what now here? Translational motion. And second is what now? The rotational motion. Means when molecule is rotating, the motion is called rotational motion. And the vibrational motion means what? The molecule will be moving what? Here and there. The molecule moves what now? To and fro. The to and fro motion of the molecule is called vibrational motion. That is called vibrational motion of the gas molecule. Is that clear? So it is about what now here? Rotational motion, vibrational motion, and what? Rotational motion, vibrational motion, and translational motion. So this type of motions will be there. Just a moment. Hold on 1 minute. Now see, this is expressed by saying that the molecule possesses what now here? Translational, rotational, and vibrational degrees of freedom. So when molecule is heated, it gets three types of motion. So now when gas molecule gets three types of degrees of freedom, what we say here? The molecule possesses, means the molecule will have translational degree of freedom, rotational degree of freedom, and vibrational degrees of freedom. So like this, 3 degrees of freedom will be obtained by the gas molecule when it is heated, when the gas molecule is heated. Is that clear, ma? So now next one, what you have to understand is that for a molecule made up of n atoms, for the molecule made up of n atoms, n number of atoms, total degrees of freedom will be equal to 3n, 3 into n. Further, split up these is as follows here. The split up these as follows. That means what now? Your vibrational degree will be there, translational degree will be there, rotational degree will be there. Okay. So for a molecule made up of n atoms. Now total number of atoms, how many? 3 are there here. Total number of atoms, suppose for a molecule, number of atoms. N is what now here? Atomicity we say. Number of atoms in a molecule is what now? Atomicity. So atomicity of the given molecule is what? N. Now total degrees of freedom will be equal to what? 3 into n. 3 into n. Number of atoms in one molecule, atomicity into 3 will be the total number of degrees of freedom. The total degrees of freedom will be equal to what now? 3 into n. Further, okay, split up these as follows here. Okay, that means what now here? These 3n degrees of freedom will be divided into 3 types here. See here, what will be there now here? Vibrational degree of freedom, translational degree of freedom, rotational degree of freedom. Now, vibrational degree of freedom will be 3 for linear molecule. For linear molecule means what now here? The molecule will be having linear shape. The molecule will be having what? Linear shape. If the molecule is having linear shape, that molecule will have how many? The molecule will have how many vibrational degree of freedom? Vibrational degrees of freedom will be 3 for the linear molecule, remember. And translational degrees of freedom will be how many? 2 for linear molecule. For the linear molecule, how many translational degrees of freedom will be there? There will be how many? 2 translational degrees of freedom. 3 translational of freedom will be there. Is that clear? So like this here, the number of vibrational degrees of freedom, and number of translational degrees of freedom, and number of what now? Rotational degrees of freedom. All these things we have to understand here. The number of so which molecule we have taken first time here? We have taken the linear molecule. Linear molecules examples what? Linear molecules like what now? CO2, C2H2, and just many different kinds of molecules are there which are linear in shape here. And next one, rotational degrees of freedom. Rotational degrees of freedom for linear molecule. For the linear molecule, rotational degrees of freedom will be how many here? 3n minus 5. 3n minus 5. So 3 into n minus 5. N is what now? Number of atoms in one molecule, atomicity. So 3n minus 5 will be the number of rotational degrees of freedom for the linear molecule. So number of vibrational degrees of freedom 3, number of translational degrees of freedom will be 2, number of rotational degrees of freedom will be 3n minus 5. 3n minus 5. For what? For the given linear molecule, if the molecule is linear shape. Next, for non-linear molecule. Non-linear molecules means what now here? H2O. Okay, so non-linear molecules will be what now? H2O. And next one what now here? NH3. These all are non-linear molecules. Non-linear molecules. Okay. Next one, linear molecules, non-linear molecules we have to consider. Now CO2 if you take linear molecule. And if you take what is C2H2 acetylene, linear molecule. So linear molecules and non-linear molecules we have to take separately. Now you see, for non-linear molecules, the number of vibrational degrees of freedom will be how many? 3 again. Number of translational 3. Okay, for linear, number of translation will be vibration will be 3 for non-linear. For non-linear, vibrational will be same. Vibrational degrees of freedom will be same for linear molecules and non-linear molecules. For linear molecules and non-linear molecules, it will be same. Vibrational degrees will be same. Okay. So what you have to understand one point here. For linear and non-linear. For linear and non-linear molecules. For linear and non-linear molecules, what will be same? Vibrational degrees of freedom. Vibrational degrees of freedom will be same. Vibrational degrees of freedom will be same. This point first you keep in mind. So here N is what now here? N is what number of atoms. Okay. If there are 3 atoms, suppose if the 3 is what number of degrees of freedom. Totally how many degrees of freedom? Totally 3 degrees of freedom. And capital N we have taken as what number of atoms in one molecule. And we have divided the molecules into how many categories here? 2 types. Linear molecules and non-linear molecules. And for these 2 types of molecules, what will be same here? It will be same what now here? Both what here? Vibrational degrees of freedom and vibrational degrees of freedom will be same for what? Linear molecules and non-linear molecules. And translational degrees of freedom will be 2 for linear molecules, 3 for non-linear molecules. For non-linear molecules, how many translational degrees? 3. How many translational degrees of freedom will be for linear molecules? 2. Next, rotational degrees of freedom will be 3n minus 5 for linear molecules, 3n minus 6 for non-linear molecules. For non-linear molecules, 3n minus 6 number of rotational degrees of freedom will be there, and 3n minus 5 number of rotational degrees of freedom will be there for linear molecules. Next, specific and molar heat capacity. Specific and molar heat capacity. So here, specific heat capacity or molar heat capacity. So first one is what now here? Specific heat, otherwise specific heat capacity. Specific heat we can say, or specific heat capacity we can say. So specific heat of a substance is the quantity of heat in calories or in joules or in kilocalories or kilojoules. Any units we can measure now. Heat can be measured in calories, heat can be measured in joules, heat can be measured in what? Heat can be measured in kilocalories or kilojoules. Okay. So now here the amount of the quantity of heat required to raise the temperature of 1 gram, temperature of 1 gram, the temperature of 1 gram of that substance through how many degrees? 1 degree Celsius. Through 1 degree Celsius, through 1 degree Celsius, if you want to raise the temperature of 1 gram, how much heat is required is called what now here? Specific heat capacity. Specific heat capacity. Now suppose you take here 1 gram of some substance, 1 gram of CO2 you take, 1 gram of CO2 substance we have taken. Now initially it is at what temperature? Suppose 25 degrees Celsius. The CO2 substance is at 25 degrees Celsius, and how many grams of CO2 substance we have taken? 1 gram. If you want to increase the temperature up to 26 degrees Celsius, now how much is the rise in temperature now? Rise in temperature. Rise in temperature, how much ma? 1 degree Celsius. That means if you want to raise the temperature, if you want to raise, here this RAISE raise is what? Verb. RISE rise is what? Noun. Okay. So the sun rises. This RISE rise. And here sun rises, RAISE rise is sun rises. But here RISE rise means what? Noun here. Okay. The rise of sun, we have to say. So the rise in temperature, how much here? 1 degree Celsius. How you said 1 degree Celsius here? Because here 25 degrees Celsius temperature is increased up to 27 degrees Celsius for 1 gram. So how much is increase in temperature? 1 degree Celsius. If you want to increase the temperature by 1 degree Celsius through 1 degree Celsius, how much heat energy is required? How much heat energy to be supplied is called what now? Specific heat. Specific heat capacity or specific heat. The specific heat means what here? The quantity of heat required by 1 gram of the substance to raise its temperature through 1 degree Celsius is called what now? Specific heat. Okay. And it can be measured. It means what now here? Specific heat. The specific heat capacity can be measured at constant pressure. If you measure at constant pressure, it is called what now? CP. CP stands for what now? Specific heat capacity. Generally, specific heat will be measured by C. It is what here? Denoted by C. C is what now here? The letter used to indicate specific heat. Now, CP means what here? The specific heat at constant pressure. And we can also measure the specific heat at constant volume, which is called CB. CB means what? C subscript V indicates what ma? Specific heat. Specific heat at what now here? Constant volume CB, and specific heat at constant pressure CP. So CP and CB, please keep in mind. So what is CP ma? Tell me. Specific heat of the substance at constant pressure. And what is CB here? What is CB here? The specific heat of the substance at constant volume, CP and CB. Okay. So next. Just a moment. So CP and CB values here, remember. The problem is just a moment. Yeah. So the specific heat at constant pressure and specific heat at constant volume. So now here, now the next one what we are taking is molar heat capacity. What we are taking? Molar heat capacity. Molar heat capacity of a substance is the quantity of heat required to raise the temperature, of 1 mole of the substance by 1 degree Celsius. Okay, here 1 mole of CO2 we are taking now. Previously, what we have taken 1 gram of CO2 substance we have taken now. Now here we are taking 1 mole of CO2 substance. So here initially suppose 30 degrees Celsius is taken. Initial temperature is how much here? 30 degrees Celsius. Okay. And now we are increasing temperature up to what now? 31 degrees Celsius. Up to 31 degrees Celsius. That means how much is rise in temperature? Again 1 degree Celsius only. So we are increasing temperature of this 1 mole of substance from 30 degrees Celsius to 31 degrees Celsius means how much is the rise in temperature? 1 degree Celsius only. Again, how much is raised? 1 degree Celsius is raised here. Okay. So like this here, what is the molar heat capacity now? Molar heat capacity of a substance is the quantity of heat required to raise, means to increase the temperature of 1 mole. Temperature of what? 1 mole of the substance by how many degrees? 1 degree Celsius. Through 1 degree Celsius, if you want to raise the temperature of 1 mole of the substance, how much heat is required is called what? Heat capacity, molar heat capacity. Now, molar heat capacity is equal to specific heat capacity into molecular weight. Molecular weight. This molar heat capacity will be shown by capital C. Capital C. Capital C at V constant volume. Heat capacity C, specific molar heat capacity is given by capital C. So molar heat capacity capital C. And specific heat capacity small c. Small c indicates what? Specific heat capacity. Capital C indicates what? Molar heat capacity. That point keep in mind. And here M is what? Molecular weight. Gram molecular weight is capital M. Capital M is what? Gram molecular weight. Now a capital CV means the molar heat capacity at constant volume is equal to, okay, specific heat capacity at constant volume into molecular weight of that substance. Take example CO2 only here. What will be molecular weight of CO2? It will be 44. And CV and capital CV. Capital CV is what now? Molar heat capacity at constant volume is equal to only specific heat capacity at constant volume into gram molecular weight of substance. Now, if you take CP, CP means what now? Molar heat capacity at constant pressure. Capital C subscript P indicates what? Molar heat capacity at constant pressure is equal to only specific heat capacity at constant pressure into gram molecular mass. Only thing what you have to remember without confusing is that capital C is what? No, molar heat capacity. Small c is what? Specific heat capacity. Here capital C meaning what? The heat required to raise the temperature of 1 mole by 1 degree. Here what is the small c here? The temperature required to raise the temperature of 1 gram of the same substance through 1 degree Celsius. Okay, to raise the temperature of 1 gram through 1 degree is called small c. And capital C is what? To raise the temperature of 1 mole of the substance through 1 degree Celsius. And M is what? Gram molecular weight. So it is relation between what? Capital C and small c. Capital C is what now? Molar heat capacity. and small c is what? Specific heat capacity. So the specific heat capacity into molecular weight will give molar heat capacity. Now, since gases upon heating show considerable tendency, ability towards expansion. Generally, gases will expand on heating. If heated under constant pressure conditions. Okay. Now, what is the condition? What is the statement we so far we said here? Since gases expand on heating at constant pressure, and additional energy has to be supplied for increasing its temperature by 1 degree Celsius. Okay, so relative to that required under constant volume conditions. So what is said is that the heat required to raise the temperature of 1 mole at constant pressure will be more than the heat required to raise the temperature through 1 degree Celsius at constant volume. So at constant pressure, the heat required will be more than what? The constant volume condition. Same 1 mole you take, suppose 1 mole of CO2 you take. Suppose I'm taking here 1 mole CO2, 1 mole CO2 at constant pressure, and also I'm taking another condition for at constant volume. At constant volume, CO2 is taken 1 mole. At constant pressure also CO2 is taken 1 mole. 2 cases. In first case here, at constant pressure, if you supply heat to this if you supply heat to 1 mole of CO2 at constant pressure, that will be called Cp. And if you supply heat to 1 mole of CO2 at constant volume to raise the temperature by 1 degree Celsius, that will be called Cb. Now, where we have to supply more amount of heat? At constant pressure, the heat required will be more than what? At constant volume. Because at constant pressure, when you are heating the gas, when you are supplying heat to the gas, when you are supplying heat energy to the gas, at constant pressure, what happens? Volume will be increasing. When volume is increasing, more amount of heat should be supplied. But here, at constant volume we have taken. Anyhow, volume will be constant. Volume will not be increasing. That's why here less amount of energy is sufficient. That's why the Cp value will be slightly more than what? Cb. Or we can say that Cp value is equal to the Cv value, means molar heat capacity at constant pressure is equal to molar heat capacity at constant volume plus the work done on expansion. So when gas is expanding, there will be some work done by the gas. When gas is expanding, what we have to understand? Some work will be done by the gas. Okay. So as the work is doing, as the gas is doing some work, here, we have to supply some extra amount of energy at constant pressure. So Cp is equal to what? Cv at constant volume plus some work done on the expansion. Okay, so that is what now here P delta V we have to take here. P delta V is what now the work done on expansion. The work done on expansion is what? P into delta V. The pressure into change in volume. Pressure into change in volume will be equal to what now here? The work done on expansion. The work done on expansion is equal to what now? P delta V. P delta V. Okay. Next. So where Cp is what now here? Molar heat capacity at constant pressure, and capital C, small v, C subscript V is what now here? Molar heat capacity at constant volume. So Cp and Cv, which is greater than which one now here? Cp value is slightly more than Cv value. And what is the relation between Cp and Cv? Cp plus Cv is Cp is equal to Cv plus some work done on expansion. This work done on expansion will be taken as what now here? Equivalent to R. R is what here? Universal gas constant. Universal gas constant R. So what we can take now this equation? Cp plus Cv. CP, sorry, just a moment. Yeah. So now here CP is equal to CV plus R na. Therefore, what we get now? CP minus CV. CP minus CV is equal to what? R. See, the difference between CP value and CV value is equal to R. What is CP here? Molar heat capacity at constant pressure. And CV is what? Molar heat capacity at constant volume. Some useful relations of CP and CV. Constant pressure conditions and at constant volume conditions. Now here CP minus CV is equal to R. CP minus CV is equal to what? R. So this is important relation here. So R value generally will be what? 8.31 for joules or 2 calories. 2 calories means exactly it is 1.98 calories R value. So we have rounded to 2 calories. So 2 calories will be R value. Otherwise in joules, if you want to mention 8.314 joules. So molar heat capacity at constant volume plus, sorry, molar heat capacity at constant volume and constant pressure will be related as what? CP minus CV is equal to R. R is what now? Universal gas constant. And now CV for monoatomic gases. Monoatomic gas example what now? Helium gas. Helium gas or all inert gases. Inert gases. Now helium, how many atoms in one molecule? One atom in one molecule. One atom in one molecule. That's why it is monoatomic molecule. Helium is called monoatomic molecule. So for monoatomic gases, CV is equal to 3 by 2 R. CV is equal to what, ma? 3 by 2 R. And it will be CV is equal to 3 by 2 plus X for di and polyatomic gases. For diatomic gases and polyatomic gases, it will be increasing. 3 by 2 plus X. 3 by 2 plus X. Where X varies from gas to gas. X varies from gas to gas. Okay. Next, CP by CV. CP by CV. Another relation I'm taking. CP by CV. The ratio of molar heat capacity at constant pressure to the molar heat capacity at constant volume is equal to gamma. This gamma is called Poisson ratio. What is it called, ma? Poisson ratio. So name of scientist is what? Here Poisson. Name of scientist is what? Poisson. So Poisson's ratio is nothing but gamma is given by CP by CV. CP value by CV value is equal to gamma. So it is what? Ratio of molar heat capacities. The ratio of molar heat capacities at constant pressure to constant volume. Okay. So it is gamma. So generally which will be more here? CP is greater than. CP is generally greater than CV na? For any gas, CP will be greater than what? CV. That's why greater value by lesser value will be positive value. Gamma will be positive. Gamma value will be more than 0. Now, another one thing. For monoatomic gas like what? Inert gas. Inert gases are monoatomic, like helium, neon, argon, all this. For monoatomic gas, CV is equal to 3 calories. 3 calories. CV value how much, ma? 3 calories. Whereas CP is equal to CV plus R. CP is equal to what, ma? CV how much here? 3. 3 plus R. 3 calories CV already we have taken. Plus R value how much? 2 calories, na? R value 2 calories. 3 plus 2 how much? 5 calories. So for monoatomic gases, especially remember, for monoatomic gases, CV value will be equal to what now? 3 calories. It is observed value. CV value is observed to be what? 3 calories. 3 calories. Is that clear, ma? Whereas CP value is equal to what now here? CV plus R. Relation it is. So from this, what we get? 3 calories plus 2 calories equals to 5 calories. Next, for monoatomic gas, means again what now? Helium, inert gas, inert gases. For inert gases, okay, gamma is equal to CP upon CV. The gamma is equal to Poisson's ratio is equal to what, ma? CP upon CV. The ratio of CP to Cv is equal to, now Cp value for monoatomic gas is 5/2R. Remember, it is Cp value. Cp value for monoatomic gas is what? 5/2R. And Cv value for monoatomic gas is what? 3/2R. 3/2R will be Cv. 5/2R will be Cp for monoatomic gas. Remember. Now the ratio will be equal to what? 1.66. 1.66 is equal to gamma here. What is this here? The Poisson's ratio gamma is equal to 1.66 for which gases? Monoatomic gases. Monoatomic gases means what is atomicity here? Atomicity. So atomicity equals to 1. Means in one molecule, one atom only will be there. In one molecule, number of atoms will be 1. Atomicity will be 1. If atomicity is 1, that is monoatomic gas. For monoatomic gases, gamma is always what? 1.66. Next, similarly, for diatomic gases, like what? H2 gas, O2 gas, N2 gas, CO gas, all this. So in one molecule, how many atoms are there? 2 atoms. One molecule contains what? 2 atoms. These are called diatomic gases. For diatomic gases, gamma is equal to, again, Cp by Cv always. The relation will be Cp by Cv is equal to gamma for any gas. Now for diatomic gas, Cp value will be changing. Cp value will be changing. Cv value will be changing. So here Cp how much? 5/2R. But here Cp is how much? 7/2R. 7/2R is what now? Cp value for diatomic gas. And what is Cv value here? 5/2R. 5/2R is Cv value for diatomic gas. If you substitute Cp and Cv, we get 1.4 here. 1.4 is what now here? Gamma. Gamma is what? Poisson's ratio. The Poisson's ratio gamma is what now? How much? 1.4. Here 1.66. Next, for triatomic gases. Triatomic gases means O3, ozone. How many atoms in one molecule? Atomicity is 3 here. What is atomicity? So atomicity is what now here? 3. If atomicity is 3, number of atoms in one molecule will be 3. For those gases are called what now? Triatomic gases. For triatomic gases, gamma is equal to what now? Ratio of Cp to Cv. Cp value by Cv. Now Cp is what now here? 8R. For triatomic gases, Cp is equal to 8R. And Cv is equal to 6R. 8R by 6R will be equal to 1.33. Gamma value of triatomic gases will be what? This one. Now, how gamma value and atomicity related, ma? If atomicity is 1, gamma value 1.6. If atomicity is what? 3, the gamma value became less, 1.33. So how these two related here? The value of Poisson's ratio, gamma, is inversely proportional to what, ma? Atomicity. So atomicity of gas and value of what? Gamma. These two are inversely proportional to each other. Inversely proportional. As atomicity increasing, gamma value decreasing here. So 1.66 monoatomic gases, 1.4 diatomic gases, 1.33 triatomic gases. Take the screenshot of this one. So Cp value, Cp formula, Cv formula for monoatomic, diatomic, and triatomic gases you must know. Now tell me, what is Cp formula? What is the formula of Cp for monoatomic gases? Cp, molar heat capacity at constant pressure, Cp is equal to 5/2R. 5/2R for monoatomic gases. For diatomic gases, what is Cp formula? For diatomic gases, 7/2R. And for triatomic gases, what is Cp formula? 8R. So these all formula we must remember. So take the screenshot of this. Next, the liquefaction of gases. Liquefaction of gases means converting a gas into liquid. In gas, the molecules will be away from each other. The gas molecules will be away from each other. This gas is to be converted into what? Liquid here. This is called what now? Liquefaction. So in this, what happens now here? The molecules come closer, not touching each other, but they come closer in liquid state. Okay, if you want to convert the gas into liquid, what we have to do? First thing what we have to do is that we have to cool. So a gas may be liquefied by cooling first. Cooling means what we are doing? We are decreasing temperature. Decreasing temperature. Temperature of gas must be decreased. By cooling, we have to do. A gas may be liquefied by cooling or by the application of high pressure. When you apply high pressure on the gas, what happens, ma? The gas will be compressed and will be converted into liquid state. Converted to liquid state. So like this, by applying high pressure, we can convert the gas into liquid, or by cooling the gas, we can convert the gas into liquid. Okay. So, or by the combined effect. Combined effect means both decreasing temperature, that is cooling, and also applying pressure. Combined effect of both. The first successful attempt for liquefying gases was made by Faraday. The scientist Faraday has first liquefied the gas. Okay, the gases were converted into liquids for the first time by whom? Faraday. What we have to first, we have to cool the gas. After that, reaching to particular temperature, we have to apply pressure and convert into liquid. That we are going to discuss in the next class. Okay, ma? Bye. Good day.